Okay, so we'll have the last talk of this afternoon. It will be by Jan Dereziński from the University of Warsaw, and it's about the Dirac-Coulomb Hamiltonians.
So
please continue.
Thank you. Thank you. Can you hear me well?
Yeah, we can hear you very well.
Yeah. So when I speak, there is no echo. Oh, okay. So I wish I could be with you. Unfortunately, a few days ago, I got a positive COVID test, so I have to stay at home. Fortunately, the COVID is very mild, but still, I have to give an. I mean, I don't have a possibility of an in-person talk, and as you can see, there are technical problems. So I would like to speak about something which is very familiar to every student of quantum mechanics too. I mean, relativistic quantum mechanics, about the fermion in a Coulomb potential. So I think most of you most of you have seen the Dirac-Coulomb Hamiltonian. That means the Dirac operator with the Coulomb potential. So I will denote by lambda the strength of the Coulomb interaction. So here alpha and beta are Dirac matrices in the non-relativistic convention. Now, it is tricky and often ambiguous to interpret this expression as a Selfadjoint operator. So in particular, without such an interpretation, you cannot compute, for instance, the eigenvalues. So eigenvalues will depend on the choice of a Selfadjoint realization. And the usual approach to similar quantum mechanical problems is to first find a domain of an operator on which it is essentially self-adjoint. I mean, this is an unbounded operator, so the choice of the domain is crucial. If we have a domain of essential self-adjointness, then such an operator extends to a unique self-adjoint realization, and we can, and then it has a unique physical meaning. Such an approach works, for instance, for the Schrödinger Coulomb Hamiltonian, so the usual hydrogen atom Hamiltonian, where we have the Laplacian perturbed by the Coulomb potential. In this case, there is the famous Cato-Relish theorem, which allows one to define this Hamiltonian. I mean, the main idea is that the Coulomb potential is controlled by the Laplacian, and because of that, the Coulomb potential does not change much the domain of the full Hamiltonian. The situation is much more complicated for Dirac-Coulomb Hamiltonians, and there exists a surprisingly large mathematical literature about self-adjoint realizations of Dirac-Coulomb Hamiltonians. So I give here a list of names, but the list is certainly not complete, and it includes some of quite famous mathematicians like Cato. Now let me describe the situation with Dirac-Coulomb Hamiltonian, which is quite complicated. So first, if you try to apply the Cato-Relish theorem naively, then you get essential self-adjointness just for lambda less than 1/2. But this is an artifact of the Cato-Relish theorem, and more refined methods extend this to the absolute value of lambda less than the square root of 3/2. So the essential self-adjointness is valid in this region. But this is not the end of the story. So for lambda greater than this number, essential self-adjointness breaks down. However, until lambda less than 1, there are two distinguished self-adjoint realizations. One of them, one can argue, is more physical than the other. So one can say that even though essential self-adjointness breaks down, the system has a unique physical realization. For the borderline case, lambda equal to 1, there is only one distinguished self-adjoint realization. And for large lambdas, there are no distinguished self-adjoint realizations, so which can be interpreted as a certain problem that, there is a separate story what may happen physically then. That is a complicated kind of series of phase transitions for this simple Hamiltonian. I would like to describe an approach to Dirac-Coulomb Hamiltonians that, in my opinion, clarifies the concept of a self-adjoint, distinguished self-adjoint realization. This is based on my recent work with Błażej Ruba from Jagiellonian University. The key elements of our approach are the homogeneity and the holomorphy. Let's try to simplify the problem, to throw away inessential elements. So first of all, the mass term is bounded. Therefore, it does not change the domain of self-adjoint realizations. So let's drop the mass term. Of course, physically, the mass is important, and it affects, of course, the spectrum. But right now we are not interested in eigenvalues. We would like just to define the Hamiltonian, and for this, to specify the domain, and for this purpose, the mass term is irrelevant. And another irrelevant feature is the dimension. So physically, the dimension 3 is distinguished, but just for mathematical fun, let's consider the Dirac-Coulomb Hamiltonian in any dimension. So massless Dirac-Coulomb Hamiltonian. So first we have the sum of, the usual kinetic term of the Dirac operators. So alpha i's are the Dirac matrices, p i's are the momenta, and we add the Coulomb potential. Now, it turns out, that one can separate quite easily the angular variables from this Hamiltonian. In fact, it is this is a textbook material how to do it in dimension 3, but you can do it in any dimension. So it is indicated on this slide. It's one introduces this operator, which is essentially the Dirac operator on the sphere. its eigenvalues are given here. So the eigenvalues are the natural numbers shifted by something which depends on the dimension. After the separation of angular variables, we obtain the massless one-dimensional Dirac-Coulomb Hamiltonian, which is written here. So in one dimensions, the spinos are two-dimensional. So it is just a 2x2 matrix given here. So this will be our main operator. So it's an operator which depends on two parameters. One is responsible for the Coulomb potential. One is the strength of the Coulomb interaction, and it is called lambda. And omega is related to the angular momentum and not only to the angular momentum, but also to the dimension. We would like to analyze this operator. So that's now. Please interrupt me if you have any questions. I mean, the talk is meant to be understandable 100%. So that's so if there is anything which is not clear, please interrupt me. We will actually allow omega and lambda to be complex. This is not very important. I mean, certainly for physical applications, omega and lambda are usually real. Now, one can solve many things about the Dirac-Coulomb Hamiltonian using the so-called Whittaker functions. So Whittaker functions, there are some special functions related to the confluent hypergeometric equation, and there are two kinds of Whittaker functions which are briefly described on this slide. But this is not. I don't want to be. I mean, please don't be overwhelmed by the identities. Now, the first fact that one can show is that in a certain region of parameters, which is described here, so if the square root, if the real part of the square root of omega squared minus lambda squared is greater than 1/2, the operator has only one closed realization. So in particular, if omega and lambda are real, then it is essentially self-adjoint on a natural domain. It is also homogeneous of degree 1, -1. So the thing that one should remember about this operator is that all terms are homogeneous of degree -1. So the derivation and also 1/x. Now I will explain actually why this strange condition appears. This will be clear shortly. Anyway, under this condition, one can compute the resolvent of the Dirac-Coulomb Hamiltonian. The resolvent, this means the inverse of this Hamiltonian minus a complex number, or if you prefer another name, the Green's function of this operator. Now, it is given in terms of Whittaker functions. The formula is quite complicated, but still quite okay. So there is an additional parameter that enters here. This is mu. This is the square root of omega squared minus lambda squared. So this will play an important role, and you should remember that the square root usually has two values differing by the sign. Now, as I mentioned, in this region, there is only one Dirac-Coulomb Hamiltonian. However, in the region where the square root of omega minus lambda squared is less than 1/2, then there are strange things that happen. Let's try to understand this region. First, it is easy to check what are zero energy eigenfunctions of this Dirac-Coulomb Hamiltonian. So for this end, for this purpose, you don't need to use any special functions. You just solve a rather easy algebraic equation, and it turns out that these zero energy eigenfunctions are spanned by these two functions. You should note that the x dependence is just x to the power mu or x to the power minus mu, and then there are there is a certain constant vector. Now, the important thing to notice is that that both these functions are square integrable near zero, if and only if this the square root of omega minus lambda squared is less than 1/2. So this is an easy computation. So in fact, let me recall that this mu is precisely the square root. Then, well, one could try to when defining an unbounded operator, one has to specify a domain. So here there are several choices. There is the so-called maximal domain, which consists of all possible square integrable functions which are mapped to L squared by the Dirac-Coulomb Hamiltonian. There is also the minimal domain. I don't well, these are kind of standard things in the operator theory. Anyway, you have you get two domains. One is smaller, the other is larger, and it is not difficult to show that if the square root of omega minus lambda squared is greater than 1/2, then both domains are the same, so there is no issue. But if this is less than 1/2, then the maximal domain is larger than the minimal domain. More precisely, the minimal domain has codimension 2 inside the maximal domain. Therefore, in this region, this interesting region, we have the following close realizations of the Dirac-Coulomb Hamiltonian: the minimal, the maximal, and a one-parameter family given by the boundary conditions near zero. So these boundary conditions mix the two possible behaviors near zero. So either we have x to the power mu or x to the power minus mu, and they are mixed with help of the parameter kappa. Kappa can be anything, and it can be actually infinity and in this case we interpret that there is no other term. Let us go back to the region where the Dirac-Coulomb has a unique realization. And so this is this region where we computed the resolvent in terms of Whittaker functions. It is easy to see that this resolvent can be analytically continued in omega and lambda inside this strange region. I mean, the analytic continuation is here very helpful, and this is why I would like omega and lambda to be allowed to have complex values, but otherwise it is not so important. So we obtain an analytic family of Dirac-Coulomb Hamiltonians. This family cannot be unambiguously parameterized by omega and lambda because we have two square roots of so there is a typo of omega squared minus lambda squared. And again this typo is repeated here. So one can try to parameterize these Dirac-Coulomb Hamiltonians by the following manifold. So the space of triples omega, lambda, and mu that satisfy mu squared equal to omega squared minus lambda squared.
Can you hear me?
Yes.
Could you repeat maybe last minute of your talk, because we lost you for this 1 minute?
Okay. So should I go back here?
No, a bit further down. When you were talking that one cannot unambiguously parameterize this region. Yeah.
So first of all, I mentioned that there is a typo here. So there should be omega squared when I'm pointing with my little hand. So there are two. So one can try to parameterize Dirac-Coulomb Hamiltonians by the following manifold. This is essentially a kind of a light cone, a quadric. So this set of triples omega lambda mu that satisfy mu squared equal to omega squared minus lambda squared. And there is we need an additional condition that mu is greater than minus 1/2. This is needed for the square integrability near 0. So this is a possibility, but there is still a problem at 0. So where omega lambda mu is 0, where the above manifold has a singularity. The correct parameter space of the homogeneous Dirac-Coulomb Hamiltonian involves blowing up the singularity. So the blown up manifold, well, its definition is quite sophisticated, and at least to my taste. I mean, it is written on this slide. In any case, this manifold is the same as previously, but the singularity is blown up in a clever way. And in this way, we obtain a holomorphic family of homogeneous Dirac-Coulomb Hamiltonians defined on this funny manifold. All these all members of this family are homogeneous of degree -1, and for in the case of real parameters, they are self-adjoint, and they describe sort of the physically distinguished Dirac-Coulomb Hamiltonians. Can you hear me?
Yes.
Okay. So I mean, on this picture, we try to to represent this manifold. Of course, only real dimensions are portrayed here. So there is a certain color code. So in particular, you can see that the red and blue parts of the manifold, they lie over the same parameter space in omega and lambda, and yellow is kind of above. So this is a manifold which cannot be parameterized by omega and lambda. It kind of turns around. Now, on the next slide, I would like to show the phase diagram of operators for various of Dirac-Coulomb Hamiltonians for various values of omega and lambda. Now, let me first show this diagram. So here again, omega and lambda are real. Lambda changes in the along the vertical axis, omega along the horizontal axis. So as you remember, lambda is responsible for the strength of the Coulomb potential, and omega is responsible for the dimension and the angular momentum. But here we consider just the zeroth angular momentum, so the so-called S wave. In dimension 1, this is a very simple case, and then omega is 0. In dimension 2, omega turns out to be, the S wave omega is 1/2. In dimension 3, which is the most relevant, omega is 1. Now, if we change the strength of the Coulomb interaction, then first we have essential self-adjointness, which corresponds to the green region. Then we cross this hyperbola, and we go into the next region. In this next region, there is a whole family of self-adjoint, one parameter family of self-adjoint realizations, and two of them are distinguished. One of them is just obtained by analytic or continuous continuation from the green region. Then we reach this line where both distinguished realizations meet. Then when we cross this line, enter the yellow region, there is no distinguished realization at all. And the same happens if lambda becomes more and more negative. So we have phase transitions when we change change from one color to another color. So these phases, they are described on this slide. So we have the phase A is where we have essential self-adjointness. So this is this green phase. Then there is the B phase. So this is between the hyperbola and these let's say, if you want, a light cone. Then the special situation is in the phase C, where C means these two lines. Then another special phase is D, So this is in the center. So this is sort of the most trivial case. And E is the yellow region where you don't have distinguished realizations, but you don't have essential self-adjointness as well. So, I mean, let me ask you what there are questions. I mean, this is sort of one of the main messages of my talk, that you can expect phase transitions in rather simple models. So that's. So are there any questions now? Let me introduce something which I would like to call renormalization group. So this is of course not. This is a very simple-minded situation, but still, I think this name is partly justified. So let's introduce the scaling transformation. Now we are interested in operators homogeneous of degree -1 or approximately homogeneous of degree -1. So when we stretch the operator, then we correct the stretching by the factor e to the power tau, and this will be called the renormalization group. Now, this group acts on realizations of the Dirac-Coulomb Hamiltonian, and so in particular, in the region A, there is nothing interesting because there is only one realization. But in regions B, C, D, and E, there are various interesting. Well, I mean, there are several distinct behaviors of this renormalization group. So let's start from here. In the region B, there are two distinguished self-adjoint realizations, and the renormalization group pushes these realizations towards one of them, towards this more physical relevant. So that's why you have arrows here and here. So this is the region B. Now in the region C, which is the boundary, you have only one self-adjoint you have only one homogeneous self-adjoint realization, and the renormalization group turns, goes from the right of this homogeneous of this fixed point to the left. Region D is quite boring, so D is the center. The renormalization group just doesn't do anything. Finally, in the region E, so this is the yellow one, the renormalization group just turns around, so there are no fixed points, but the scaling symmetry is broken to a discrete scaling symmetry. So that's is this picture understandable?
I assume so.
Now, you can compute various other things about Dirac-Coulomb Hamiltonians. For instance, one can diagonalize them. So diagonalizing in quantum mechanics often means some kind of scattering theory. So now the Coulomb potential is long range. So this is actually not the simplest scattering theory. In any case, one can define two Meller operators. One is kind of incoming and the other outgoing. And Meller or wave operators, if you want, they are now they differ by a scattering amplitude, which can be computed exactly. So I mean, on the slides there are formulas for the scattering amplitude. No, well, the Meller operators are quite complicated. So I mean that again, I'm providing complete formulas, but you should not be scared by them. So they can be computed in terms of the hypergeometric function, and also the operator A, which appears here, is the generator of dilations. Now there is well, maybe this is not so. I mean, the relevance of this is not so obvious, but I mean, I believe that it is important to understand analyticity properties of various objects. So here, everything can be extended analytically. So even if you're interested in the Selfadjoint case, you may be happy that things are analytic. Also away from the Selfadjointness case. However, and in particular, these Meller operators can be analytically extended, but they become unbounded. At least unbounded if so they are bounded only if lambda is real. Lambda was this coefficient in front of the Coulomb potential. So this is an expression of the fact, and if lambda is 0, then they are always bounded. This is an expression of the fact that the angular momentum perturbation is effectively short range, unlike the Coulomb potential, which is long range, even though both decay like 1 over the radius. Now, this is essentially the end of the story about Dirac-Coulomb Hamiltonians, which I wanted to describe. Now, let me mention that there is a similar story, similar but simpler, about the so-called Bessel operator. The Bessel operator is the second order operator given by this formula. So it is a Schrödinger operator, not a Dirac, but Schrödinger operator with the potential 1 over x squared. This is also enters in many quantum mechanical applications, and now but it also has phase transitions. So now here it is you have only one parameter which is denoted alpha, and it turns out that there are two phase transitions here. One when alpha is equal to 1, and the other if alpha is equal to 0. And you have essentially the same action of the renormalization group in the case of Bessel, of the Bessel Hamiltonian. So this is essentially the same picture, and like this one, there is no analog of this region D in the case of the Bessel Hamiltonian. And so I find these examples quite funny and instructive. So I try to promote them by attaching pseudo-physical names to these spaces. So when you have only one self-adjoint realization, I say that this is the gaseous phase. When you have two distinguished homogeneous realizations, but then one can call this liquid. And when you don't have fixed points of the renormalization group, because the scaling symmetry has been broken, then one can call it a crystal or a solid. But you can judge whether this terminology makes sense or not. So what are the messages of my talk? Well, there is one obvious physical message. So there may be problems with strongly charged ions. If you have, if you have an ion which has a very strong charge, then the corresponding Dirac-Coulomb Hamiltonian will be problematic. So this may have some physical consequences. I mean, of course, such nuclei are unstable for other reasons. So this is not a very physical consequence. The other consequences are more mathematical, but they are also interesting. So boundary conditions can be very tricky. So this was a very simply looking Hamiltonian, well, essentially all my talk was about the boundary conditions. The third message: homogeneous objects have special properties. So both the Bessel Hamiltonian and the Dirac-Coulomb Hamiltonian without a mass are homogeneous, and this has various interesting features. Another message is that it is useful to organize things in holomorphic families. This is what I believe is a good tool, a mathematical tool which organizes things. And finally, simple mathematical objects like Dirac-Coulomb Hamiltonians may have unexpected phase transitions. So that's all. Thank you for your attention.
Thank you. Do we have any questions? So is there any hope for having experiments that would, for instance, test which Hamiltonian is the right one?
I mean, you would have to produce a charge which has a very strong, so it's essentially this a charge which is greater than the inverse of the fine structure constant, and this is I mean, such nuclei are unstable. So this is not a very physical question. I mean, so in the parameter range which we are in, then there is a uniqueness of the Hamiltonian, so there is no such issue.
I see. Yeah.
Quick question. How much these results depend on the dimension?
Yeah, so let me this is this reduction was valid in any dimension. Now in dimension 1, there is essentially no issue. So the omega is 0, so there is nothing interesting. In dimension 2, if you look at S waves, then you have this line, and so this line does not enter the green region. So in the so in dimension 2, you don't have as you are always in a problematic zone. So maybe there is some physical relevance for the Coulomb problem in dimension 2. So that's in dimension 3. Then you start with this unproblematic region. In dimension 4, it is even so that's this is the picture.
Okay, and other questions?
And this separation of variables, this is actually quite funny. So that instead of using the angular momentum square, you use this operator, and then everything works.
Okay, if there are no more questions, let's thank Jan again. This concludes this session.